Hello, I'm Chris Rackauckas, and today what we're going to talk about is how to debug Julia simulation codes. This is going to be a deep dive into ODEs and how ODEs are then used with optimization, but the general principles here should be rather translatable beyond Julia and also beyond just ordinary differential equation simulations, right? So I really want to kind of give the high-level ideas of how someone really digs in to find out what's going wrong with the code and what the kind of issues you need to worry about are is in the cases where you have simulation, so when you have equation solvers involved. Julia has fast differential equation solvers, and we talk about how, it's 50 times faster than SciPy, 50 times faster than MATLAB, et cetera, but nope, that's not the topic that we're doing today, right? We're going to be talking not about performance. Today we're going to be talking about just how do you make sure that your model is correct. This is the common problem, right? You build a model, you want to simulate the model, and you look at it and it just doesn't do something that you expect it to. So for example, you're like, I built a model of a population and the population increases over time. I thought the population was supposed to be constant and now I'm mad, right? Now, once you figure out that your simulation is doing something you didn't expect it to, what do you do about that? Before we dive into how you do stuff, right, I first want to talk about where can you go to learn more, right? So JuliaCon is a great place. JuliaCon videos are a great place. You've shown up to the right place, but there are also other places to look. So the discourse.julialang.org has a lot of very good resources. In fact, before you post onto the forum, please search for your issue, right? You might see something like, dt minus less than or equal to dt min. Search for that. Read some of these other issues. See what other people have ran into. See how they've solved it. There's a lot of really good resources around for that. And then the other thing to know about is that there's an FAQ section in all of the SciML documentation. So all of the solvers, right, the solvers that you use for differential equations, optimization, integrals, all of these packages have an FAQ section, right? This is why SciML kind of standardizes the way it does its documentation. So if you have a question, look at the FAQ. Those are the frequently asked questions. Most likely, because it captures the frequently asked questions, most likely that's where your answer is going to be found. Now, if you don't find your issues there, then of course post into the Slack, post into the discourse, post on Stack Overflow, and we'll make sure to help you find an answer. But in order to make sure that you post onto those correctly, I want to show what kinds of analyses and things you should be doing before you even start to share with someone else. There are two types of issues that one can really run into when modeling, right? So models can either give the incorrect output in some definition of incorrect, or they can have a type 2 error, which is model code throws an error, right? It's just you run the code and it does something, it throws you an error, and you're like, okay, I don't know how to deal with this. We'll start with this type 1 error, right? So this is the error where you say, I think I'm implementing my model correctly. It gives me an output like, oh, I expect my energy to be constant. The energy grows over time. Something is going wrong here, right? And the first thing to do is to try to assign blame, right? Is it an issue with the solver package? Is it an issue with this other package? Or is it an issue with me, right? 99.9% of the time, it is an issue with the way that the user has written the model. So I'll tell you that right there that most likely you made a problem, but that is not a good enough answer, right? You want me to be like, okay, how do we actually show that it's a user issue? One of the nice things with differential equations.jl is it's not that hard to prove if it's a user issue or a solver issue. Because, when I talk about all these benchmarks, right, notice in here I mentioned that, hey, there's all these methods from C, Fortran, SciPy, MATLAB. So, you can think about these as useful for benchmarking, but actually the real use case for having all these wrappers is with debugging. If you have all these differential equation wrappers with you, try them, right? So here, for example, this is the Lock-Volterra equations. I slap some keyword arguments on it, and here I solve it in Julia. I solve it with the sundials from C. So this is a completely different implementation created in 1990 or so. And we're calling that solver with this function, right? Here's Harris Fortran method, right? We call it with this function, right? MATLAB diffeq, right? So we actually have a way to take this code, translate it into MATLAB code automatically in a lot of cases, and then call MATLAB's ODE45. And so, okay, we solve it with MATLAB. We can directly call SciPy with this function, right? So there you go. There's 5 different languages of solvers. And the main reason why you would do this is because this can very easily highlight if there's a solver issue, right? I'd like to describe this with a meme, right? You don't want to be like Patrick here, where you just go, okay, my model diverges. Say your solution diverges to infinity, and you're like, okay, it does that with the C++ and Fortran ones, right? It does this with the LSODA is a solver from 1980, and Dasker's a solver from 1980 as well. And if you try all these solvers and they're all diverging, there's 2 things that can be true. One is that every single solver that's ever been created is incorrect. Or 2, the model that you spent the last 20 minutes writing might have a bug in it. Normally, it's 2. I'll go into some more details, but basically, this is a very nice way of being able to just highlight, like, hey, is there a solver issue? Or if every single solver does the same thing, you probably have to suspect that there's some issue with the way that the model is defined. Now, every once in a while, this will highlight a solver issue. I mean, it's not just, in the Julia ones that are newer, but also in C and the Fortran ones, we found bugs all the time, right? The no code, even codes that have been looked at every single day since 1970, have some bugs in them. I've found them. So, if only one solver is different from all the others, that's worth an issue. That's worth open up an issue. Tell us about what you found. This is something that this is how we highlight and discover things that go wrong in the C code, the Fortran code, and the Julia code. If one of them are very different from all the others, that's a solver issue. If some of them are different, most likely the issue is tolerance, right? So here in this example, notice that I changed the tolerance. I put the keyword arguments for abstol, reltol sufficiently small. The solvers are only guaranteed to converge to the same answer as delta t goes to 0, as the tolerance goes to 0, right? If the tolerance is sufficiently high, then there can be differences in the solution. And so when you do this, make sure that you actually set your tolerances low enough. And a way to be able to see whether your tolerance is not sufficiently low is just if if you have a group of solvers that have a different solution from another group, right? If there's one odd one out, that solver might be an issue. If there's a whole group of them, group A, group B, then reducing the tolerances will almost certainly make those be the same. Now, if all of the solvers are the same and they are all giving an incorrect result, well, then probably what you're putting into the solvers is suspect, right? That's most likely going to be the issue. If you really want to then highlight that, hey, this has to be a model issue, one of the things that you want to do next is you want to actually go through the stiff ODE solvers and some of these more robust methods, right? So TRBDF2, this is a method for stiff equations. Rosenbrock 2.3 is a ABL stable method over all of its orders, right? So, this is a very robust method. If these methods are also failing, then you can be very suspect that the issue is with your model. A lot of times people might not know that their model is stiff, right? And so if you can do this, you switch the solver and suddenly what looked like a numerical issue goes away. So before you declare that your model is non-stiff and it has an issue, double check. Just run it with the stiff ODE solver and see what you get. Now, one of the things that can happen with a stiff ODE solver is, the reason why a lot of times, you kind of start with non-stiff ODE solvers, because non-stiff ODE solvers are a lot faster, and they also have a lot nicer properties with the scaling. So, for example, a stiff ODE solver will require building a Jacobian of to size n by n. If n is very large, say n is 10,000, a non-stiff ODE solver will just run just fine. There's no Jacobian. But with a stiff ODE solver, then there's an n by n, a 10,000 by 10,000 matrix that's being created. And so you can look through the docs, and you might have already looked through and seen that when you work with stiff ODE solvers, you have to define sparse matrices, etc., to make them fast. But if you're just trying to do the debugging process, it can be very helpful to make use of something called the GMRes method. So you can take a stiff ODE solver like TRBDF2 or CVODE BDF, and you can say that the linear solver should be GMRes. When you do this, it's now going to use a Jacobian free method. It's already going to be specializing on sparsity by default. While this is a bit less stable of a method than the standard linear solver, this makes it so that way you can apply it to, say, an arbitrarily large ODE without worrying about defining sparse matrices for Jacobians and all that, right? So if you have a very large system and you just want to try a stiff ODE solver, slapping GMRes in there is a nice trick for just being able to run one. And now another trick is for semi-stiff equations. Rock2 is a very nice method. It's a explicit method that has a very large stability region, and so it has more stable properties. And so this is a nice case to be able to tell you like whether you're moving into this instability regime. I'll highlight here that Rosenbrock 2.3, Radow IA5, and the Radow methods. These are some of the most robust solvers, right? So one of these is a Fortran method. So these are methods that you really want to kind of try before declaring that there's any kind of issue. And also, you can always try with CVOD BDF. BDF methods are not as stable as something like a Radow method, but it's still also kind of a classic method, a nice one to try before declaring that you have some issue, right? So always when checking the solver, check the solver properties, right? I thought it was a non-stiff ODE. Does it actually work with a stiff ODE solver? Another kind of property that can come up is something that might need a special integrator. So if you need something that enforces conservation laws, you might need to use a differential algebraic equation or callbacks. Another case that comes up is methods for long-time integration. I would suggest checking out this computational science stack exchange post where I go into detail on symplectic integrators. But essentially what happens is symplectic integrators have extra properties for ensuring some periodicity in some form. I'm not going to go into details here, but basically it means that for very long time integrations, they can reduce the amount of error drift if it's a Hamiltonian system. So, if you have certain types of properties and you're doing something kind of odd, then you might need to use some kind of special integrator to have all the properties you'd expect. That's just a property of integrators. So, okay, if you go through all this and you see that I know that the solver is not the issue. I've tried everything in C, Fortran, symplectic, non-symplectic, stiff, non-stiff. All of them solve and they all have the same exact issue, right? If that's the case, then it's most likely you're the issue. So in this, when we've narrowed it down to this, what do we do now? So this is step number 2, right? So after we've isolated the problem to being about the model, now we look into common model issues. And so if it works in MATLAB, Python, and R, but not Julia, right? So if your claim is I made a translation, my model was working before, now it's not working. The first thing to double check is that make sure that your model gives exactly the same results, right? And when you do that, first of all, check your parameters, check your initial condition. Don't look at the code. Look at the actual values that it gives you, right? So, if you have some code that generates your parameters, print out them to the REPL, and then, check out the printed values here, check out the printed values in MATLAB, make sure they're exactly the same. I can't tell you how many times I've been helping someone debug their code, and literally just the parameters are different values. That happens all the time, so double check that first. And the next thing is make sure that your model produces the same values in the 2 languages on a random input. Why a random input? Because it can be very easy. A lot of times your initial conditions are very easy, right? They're like 0, 0. Well, on the case where your values are 0, 0, you might have some special things, like you have values cancel, and when values cancel, you might not see that, for example, a parameter is incorrect. Right? But if you do it on a random input, you're much more likely to not have all this cancellation, and you're much more likely to find that there's actually a true difference in your equations. So take what you have, after you found out that your initial conditions and your parameters are correct. The next test to do is just change them. Say here, make my initial condition something random, and just make sure that here's the value I get in Julia. Make sure that here's the value you get in MATLAB. I'll tell you that more than 90% of translation bugs on Discourse, you'll find that when they get to this step, their issue goes away, right? Their issue becomes like, oh, I realized that actually I had a minus sign where it had a plus sign, right? So this is the key debugging step. Please do this one. If there's a complicated function call, right? So let's say you're doing an interpolation inside of here, or you're using some special integration inside of here, right? If your function is doing something that's kind of difficult, One thing that you really should try is use a language wrapper call. So, pycall.jl, matlab.jl. Directly call that interpolation function. Don't be like, oh, interpolations.jl is a lot like scipy.interpolate, so it should be similar, right? Try to reduce all of the things that can go wrong by making it exact, right? So directly call scipy interpolate inside of here using pycall, and you might find that your issue goes away when you do that. In which case, the issue is that interpolations.jl was being used incorrectly or was not doing the same thing as scipy.interpolate. Now you've isolated your issue to something that doesn't have the ODE solver involved, and that's much easier to debug, right? So, really, really, really hone down and get the values exactly the same, right? Make it so that way you have exactly the same thing coming out here as you did in your original code. And after you do that, if you still have some different behavior, then decrease your semantic surface, right? What I mean by that is do as few weird things as you can. So, so here's a bit of a weird thing, right? U equals XY. So this is a dereferencing. Maybe get rid of that, right? Just use U of 1, U of 2, right? If you decrease the amount of language features you're using until you finally find out which one is causing the difference between the language that you're more used to. I will tell you what the most common issue that I've seen is. The most common one is mutating U. So I've seen MATLAB codes before where as you're solving, they go, I actually want to change the value of U before I calculate the derivative. There's a reason why this actually gives a different value in Julia than it does in MATLAB. The reason is because in MATLAB there's copy on write. So the moment you do this mutation inside of a function call, it'll create a copy of U. And so this is on a copy of U, and it doesn't actually affect the U inside of the integrator. Whereas in Julia, it actually does a pass by reference, and this will then change the value, right? And so if you decrease your semantic surface and kind of get rid of anything that can go wrong, you'll find out like, oh, this line of code is the line of code that goes wrong. Now, the funny thing about this issue is that if you're doing this in MATLAB, it's actually not changing U because of this copy on write behavior, and so your MATLAB code is actually the one that was doing something different than you thought. But generally, you should not be doing this inside of an integrator at all. But this is just to highlight, if you have a translation, this is how you find out what's going different in your translation. And if you then can't highlight it, then please, share the Julia code and the MATLAB code, and we can go through side by side and see how come they can give the same result as a function, but not the same result as an integration. Once you've made sure that you've translated everything to the correct functions, your model might still not work, right? It might have been incorrect in MATLAB, and now it's incorrect in Julia, right? Your model's just diverging everywhere that you've written it. And now, if this is the case, double check that if you're violating any ODE solver assumptions. Almost all ODE solvers make the same assumptions, and I'll showcase why this is done. So here's, for example, on this lock Volterra, remember I'm mutating U. This is a bad thing. ODE solvers generally assume that the value of the ODE is not changed within the function that calculates the ODE derivative. So if you're doing this, don't. This is one of the assumptions, and I'll go into why this can fail. Another assumption that a lot of ODE solvers make is that your function f is deterministic. ODEs are deterministic. They expect that your function f is deterministic. If your function is not deterministic, then the adaptivity will have very big issues trying to figure out what the true deterministic solution of your equation is, because it's not a deterministic equation. If your function is not deterministic, like you're adding a random value, most likely what you're trying to solve is an SDE or an RODE, and you're using the wrong equation, right? This is the general fact that a lot of times if you are doing something a bit weird, you might be solving the wrong equation, and you might need different solvers. Another thing that comes up is purity, right? So differential equations assume that every time you call f on the same inputs, you get the same answer. Derivative of u at a given time point should always be the same value. It shouldn't be two different values. Very much related to stochasticity issues. So here's a case where non-purity shows up, where you say, oh, I cache a value from the previous time, and I want to use the u of u minus delta t here, and so I cache it into here, and I use the previous one, right? Or maybe use the previous one from a previous time step or something. Don't do this. If you're trying to use a previous value, then you're probably solving a delay differential equation, and in which case you need to use this delay differential equation. In fact, this is not doing what you think it's doing at all. Let me go into a bit about why. If you understand a little bit about ODE solver adaptivity, you'll suddenly be able to see why these things will give issues to it. So what happens in a adaptive ODE solver is you first propose a time step, and then it tries to do is two different solutions, right? It tries to solve it in two different ways at t plus delta a, or t plus delta t, and then it approximates the error using the difference between them. And if that error is too high, you reject, and then you make a smaller time step, and then if this error is low enough, then it accepts the step. Now, think about it. If your function is not deterministic, and every 2 times you call it, you get different answers, well, then this is going to be random, right? And that randomness will be the minimum distance you can have. And if that randomness is too high, if it's higher than the error estimate that you're trying to hit, the tolerance that you've chosen, then it does not matter what delta t you've chosen, you're still going to have a difference. And so what will happen is that the integrator will keep on rejecting steps. It'll keep on thinking the error is high. It'll reject steps, and it'll keep on pulling back until it says, well, dt is less than dtmin or nan dt, right? That's where that will come from. And now notice that if you have a non-pure function, then your ODE is not always solving forwards, right? So here it calculates forwards 2 times, and then it goes backwards, right, to be able to solve back here. And so if you are trying to cache values, assuming, hey, this is my previous value, it might not actually be a previous value. It might be a value from the future, right? It might be a value from a future from a rejected time step. And so this is why, these kinds of hacks on ODE solves will not do exactly what you think they will do. Not only is your delta t changing, and so the definition of what previous delta t is undefined, but also it's not always moving forwards. So hopefully that highlights a few things. Now, the next thing to really worry about is, does your ODE have a certain degree of regularity or smoothness? ODE solvers always assume some amount of differentiability of the solution. And if you violate this, then you will have some issues with the way that that the solver works. So here, for example, one way to highlight this is that lower order integrators will always have less smoothness assumptions with them. And so if you see a second order ODE solve that's working, but then you move to, like, say, SIT5, a fifth order ODE solve, and it's not working, most likely there's something broken in the regularity or smoothness assumptions. And one of the things that can cause this is if statements, maxes, and mins inside of your f, right? Because these statements are discontinuous, right? If t is greater than this, less than this, then you'll have a discontinuous change. And one of the things that you can do to improve code that has that is to take that discontinuity and make it smooth. Right, so here's an if statement. If x is greater than 5, it's v1, otherwise it's v2. Instead of doing that, you can use, for example, tan h to create a function that looks a lot like your if statement, but instead is doing this to change smoothly. You can do this then, for maxes and mins. And if you go through this discourse post, I post all the different ways you can do this smoothing. Now, one of the other things that you can do in this kind of case is make use of a callback, right? What you can do is you can place a callback so that way when the discontinuity is hit, then you have the integrator step exactly there. If you force the integrator to step at these discontinuity points, it will improve the convergence, and it will also improve the numerical stability. So using callbacks is another way to handle this. Another thing that might come up is that you might see some nans or infs. If you're doing this with a stiff ODE solver, one of the things that you might want to do is turn on forward diffs nan safe mode. It's documented in the forward diff documentation. Turning on nan safe mode will turn some of its nan derivatives into direct zero. So when you're, like, for example, dividing by 0, turning on nan safe mode will make that change from a nan to an inf, and it might give you better information. The last thing is differential algebraic equation solver. So when using a mass matrix and stuff, they have a maximum index, or maximum allowed index. And you might just go, what the heck does that even mean? Well, this is only for the DAE case, but it's important to kind of know. So if you're writing down a ODE that also has a constraint equation in there, right? If you're trying to do this, then it's a differential algebraic equation. And most DAE solvers make the assumption that the DAE is index 1. And a nice way to be able to eyeball whether it's index 1 is that any algebraic equation should be dependent on some algebraic variable. So here's a pendulum, right? So there's x, the velocity in x, y, velocity in y. So it's a two-dimensional pendulum with a tension and a length. So tension is the fifth state variable, right? How does the tension change over the time? Because the length is constant. X squared plus y squared is L squared, which is the length constant. But this is an algebraic equation that is only dependent on the algebraic variables. So therefore, this is not an index 1 DAE. In fact, if you differentiate this equation and then you substitute the other equations in, you can rewrite this into exactly, this is exactly the same system, just rewritten in a different way, where now tension shows up in the algebraic equation, and therefore it is now an index 1 DAE, and this will be more stable to solve. If you don't know any of the details about this, you might want to use a modeling toolkit when doing differential algebraic equations, right? But this is a nice eyeball test for whether, if you write down a DAE, whether it's going to be a stable solve. And here's actually this case in action where you define this pendulum, you solve this pendulum. It will use a stiff ODE solver by default, but it will still say, hey, I couldn't solve this. This is just a property of stiff ODE solves, but you can use modeling toolkit ties to turn it into a symbolic system, tell it to structural simplify, which will do this transformation automatically. It'll discover how to do the optimal way to rewrite your equation, and then when you solve it, it'll get the right answer. So if you're doing DAEs, I think the simple answer is use modeling toolkit, but the also non-simple answer is here's a good eyeball check. One of the last things to really understand is that if your model is diverging, double check your assumptions. So a lot of times people will look at this equation and say, hey, my model diverges, and it's like, well, if u is greater than 1, then your derivative is positive here, so therefore it's going to diverge, right? That's just a property of your model. One assumption I see a lot of people get wrong is that, hey, u prime equals minus square root of u. This goes to 0, so this ODE, it should always stay positive, right? This is wrong. You can only assume that your model will stay positive if the influence on the derivative is linear. If it's square root like this is an equation where the solution will hit 0 in finite time, and in that when it hits 0, the solution is no longer unique. It's either complex valued or it stays 0 forever, or is quadratic. Like this was the one that, this is one of the 3 analytical solutions it can find. So if you say have a Hill function or a Michaelis-Menten, and your solution, you think it's positive and it actually hits 0, it might actually be an equation that actually hits 0. So, really think about the mathematics of your equation. This is one of the big assumptions that I see people go wrong all the time. And if you don't know what's going on with your equation, check the values. Just look at the values, print them out, and see, hey, this term, this term, this term, oh, this term is bigger than this term, so therefore I have a negative derivative. At show is a very nice mechanism for then looking and climbing through a simulation. So that's all type 1 errors. So what about, so let's go into type 2 errors, right? So for type 2 errors, what you want to do is you want to isolate the problem and build a model, MWE. So what is an MWE? It's a minimal working example. So it's a minimal bit of code with the issue that is there to be worked on. You want to give someone something so that way they can copy paste it into their own REPL, they can see the error, and they can start working on it. I mean, if you post a GIF of a piece of code in a Pluto notebook that has data that no one has access to, then no one can run your code, no one can help you debug. So give them something that you can copy paste and try themselves. So when you do this, cut out everything that's not necessary. Replace any data with just fixed generated input, right? The key here is that we actually don't care about calculating the values correctly. If we see an error, in order to figure out what's going on with that error, the values don't matter. All that matters is the type of code, the structure of code. And so you want to cut out anything that is hard to get, all your hard data and everything, and just find the minimal bit of code that gives you the same error. And I'll show how to do this with a live demonstration. So I'm going to now go into a live demonstration and showcase how you do this on a very common problem. Now, if you're watching this as part of JuliaCon, thank you very much. This is the 30-minute mark. But if you have some extra time or you're watching this at another part, well, now we're going to go into some live debugging and really look at how to create minimum working examples on an easier case and a harder case and really understand what's going on with some Julia stack traces. Okay, so here we go. We're trying to figure out what's going wrong with our code, and oh god, we have one of these big stack traces that has a bunch of forward diff all over it. So what do we do about this? So the key here is really to minimize your problem, right? You really want to find out what's going wrong by trying to remove anything that doesn't truly matter. So when I start to look at this, this is a model of a partial differential equation, but that doesn't truly matter, right? So let's start cutting things down, right? So we're using we're using 100 by 100 matrices here. Does that actually matter? No, it doesn't matter for this error. So let's really cut this down. So for starters, this whole tridiagonal matrix, I mean, to get the right values, you have to use this tridiagonal matrix. But to figure out what's going wrong with this error, I think I can just replace it with just some random matrix there, right? So I can probably even cut out this extra information here. So let's try this, right? So I tried this, and we'll recompile, and then what we'll see is, oh, I get the same error. So I'm honing in on it, right? I'm reducing the complexity. What else can I reduce the complexity of? Well, if the error is right here, then let's see. Maybe I don't need a lot of the other parts of this definition. Maybe it's much more complex than I need it to be. So let's cut out our parameters entirely. Let's get rid of all this parameter stuff. And these equations, maybe all I need is the result here to be able to hit the issue. So maybe I just grab this and I delete everything else. And let's see, let's hope and pray. Haha, still got the same issue. I mean, it actually took a few steps in there, right? It was doing something, but it still hit the same exact issue. Now these variables are unused. I can actually delete them. So I can actually delete here, and I can delete here, I could delete here, I could delete here, and oh hey, actually this was an equation that had a 100 by 100 by 2. It had a part that is u and a part that is v. Maybe I can get rid of all that as well. So maybe I can turn this just into an equation on one of these equations. I can make that 0. And now I would just have u is equal to r. U is equal to r. I can delete this line. I don't have any v left. I can delete here. I can delete here. And I can say that, du is now dr. I can do this, right? Let's hope and pray that we got this right. Aha, we still have exactly the same issue, right? So we're honing in on it. We're trying to understand it. Now, let's see. Oh, I'm not using this matrix anymore. This is now zeros of n to n. And I'm not using this anymore. And I probably don't even need the n to be so large. Nope, I've made an issue here where is that? A has dimensions here. So how do I read this, right? So this is in the gem wrapper. So this is in the molbang. So when we look at molbang, right, it's CAB, which means that A has dimensions 100 by 100, B has dimensions 2 by 2, which means that AY has dimensions 100 by 100 because the one that I redefined is AX. Okay, so that's how you read the stack trace there. And there we go. Boom. Now we have this issue, right? That whole PDE that I had before, all those huge lines, the actual issue is this little tiny thing right here, just about 10 lines of code, is this exact same issue. Now, one of the other things to do here, remember, is always isolate. Always identify what is going on by isolating your problem. So, well, we have a stiff ODE solver. Issues are with forward diff tags. So why not change it to auto diff equals false? That gets rid of the automatic differentiation. That gets rid of the use of forward diff. And we see that, aha, this works. So now we've honed in on the issue. It is automatic differentiation of the solver when computing the Jacobian, with automatic differentiation, this will err. Without automatic differentiation, this will not err. If you can figure out why this is the case, then you'll understand how to fix your original code, right? And I'll tell you the answer because this is a common problem that people run into. If you look, and its a solution is something called pre-allocation tools.jl, right? So what's going on here, and how does pre-allocation tools become the solution? Well, the way to really investigate this is I would do @show type of dr type of r, right? You know, it's saying that there's something to do with types in here. So let's actually look at what the types are. So when we run it, what we'll see is that you know, it runs, and for a few times is going to call this with R being a matrix of float 64 and dr being a matrix of float 64. But suddenly what will happen one of these times is that R and dr are both going to be matrix of dual numbers, right? Dual numbers are this thing where it's from forward diff, right? So you can actually go look at this and you can read through forward diff.jl, right? This will tell you more information about that type that you hit. But so what's happening here though is that we have at some point R and dr become forward diff.duals. And so this is a forward diff.dual. This is a constant matrix of forward diff or float 64, and then this is a matrix of float 64. But if we actually look at, let's actually try this out. AX of 1 times R of 1, right? Let's actually look at this. So AX of 1, R of 1. Right, so when we look at this, what we see is that AX of 1 is a forward diff.dual number, or AX of 1 is a floating point 64 number. R of 1 is a dual number, forward diff.dual, and then the multiplication promotes to a forward diff.dual. And so what this is telling you is that float 64s can promote to forward diff.duals, but forward diff.duals cannot promote down to floating point numbers. So that's actually what this error is saying, that it's trying to take a float 64 and or it's trying to take a forward diff.dual and turn it into a float 64. Why is that happening? Well, because the result of this multiplication is being put into AY of U, right? So, you know, we're doing a mul bang operation, so this is right into AYU, AX times R. So when we do this, we should now actually be able to minimize the error even more and see that, well, let me cut this down here. We can minimize this even more and see that the error happens now on this line, right? We don't even need to do a mul bang operation. We can just see that the real underlying issue is that we cannot take a forward diff.dual and put it into an array of float 64s. Now, this is a known issue. This is something that if you are building caches outside of your equation, you need to worry about this. The solution is to build something called a dual cache. Right, so instead what we do is we say AYU is equal to a dual cache of zeros and something that is a chunk size of, say, 12. 12 is always going to be the upper end, so it's a safe version. And now instead of using this, if you follow the pre-allocation tools.jl documentation, it'll tell you that if you do this, I'll show you what it does in a second. If you do this, underscore AYU, it's going to give you underscore AYU, and this is going to be something that can act on. So let's actually look at why. So @show type of underscore AYU, type of AYU, or type of R. Right? Let's see what this is actually doing. So here, when you have a matrix of float 64, the dual cache, what it will do is it'll give you a cache type of float 64. But when you have R being a matrix of dual numbers, then it's going to grab a cache type that is based on dual numbers, right? And because this is now matching types, the underscore AYU is fine as a cache to be used in this equation, and so it's able to continue onwards and finish the solve. Right, so that fixes the issue. And now once you notice that, oh, this is the solution, this is the fix, then you can go back to your original code and turn it into something that uses dual cache and be fixed. But what I really want to highlight here is, if you didn't know the issues with forward diff and all that with pre-allocation tools, I want to just highlight that because I know it's a common issue. But if you couldn't figure that out, that's fine, right? Once you have the issue to this point right here, right? Once you really understand, like, oh, there's something going on here, this is a minimal example, right? This is a nice thing. You take this, you copy paste it onto Discourse, and you say, why does this have an error? And this is a nice 10 line example that I or someone else will then copy paste onto our computers, run it, look at it, and then explain to you why this error exists. So this is what we call a minimal working example, because it's very easy for someone else to work on this. The more minimal your example, the much faster of a response you'll likely get from people who are looking to help you, because someone needs to do this in order to help you, right? Either you will do it to your own model, or someone else, when they take your problem, they will do this on their own computer. But if they have to spend more time to be able to do this, then it's likely that they will not help, right? And so if you make their time commitment as small as possible, it's more likely that you'll get help quicker. And so doing this process is very useful, A, for your own understanding, but B, to reduce the time on and help out the people who are trying to help you. And now I'm going to kick to a much more difficult example where I'll go into building an MWE of a case that has a parameter estimation with Zygote and a lot of other details involved. So let's take a look at debugging a very difficult error. This came up when trying to update a version of Flux, and so sometimes you see something deep in the weeds. So what I did was I took a look at these tests, and I wanted to isolate out this test error, right? So stiff nested AD test, I take a look at this. Hey, look, it's right here in this file, and it has some gigantic long stack trace. I have no idea what's going on here, right? So how do I figure out what is actually going on with this kind of issue, right? So what I did first was, you just take a look at this and you see, hey, here's the test right here. This is where the issue is. So pull this out, right? So everything in the SciML ecosystem always makes sure that the tests are just directly copy-paste runnable. And so you can directly just take this, copy-paste. I put this over in my test.jl file, right? I just like to always run things over in test. So now let's run this. And when you run this, you just run. And what you'll see is you'll be able to recreate the error, right? So how do I make sure that is actually true? Well, you need to do something, which if you take a look at these tests, this is using safe test set. Safe test sets are actually a lot safer than other test sets because they create a module in which case everything that can only be used, you can only use features and functions and things defined within that test script, which means that every single test script can be copy-paste ran like this. So that's just a point. I mean, a lot of test sets, you can do this without safe test sets, but you'll have to figure out all the dependencies, etc. So here I copy-pasted it out, and what do you know? I got this error, right? So it's actually such a big error that I can't even scroll to the top of the stack trace, right? This is insane. So what I can do though is here I can scroll over, and down here I can start to see, oh, hey, so there's something in Zygote's optimizers. I'm not quite sure what that is, because I haven't been developing that. But down here is the first thing that I recognize, right? So I'm looking in here and I see that it's calling into my function that I've defined, and the real meat of it looks like it's going to be in this derivative wrappers function. So this looks like it's a possible way to understand what the error is, right? Somehow, when I call back right here, which comes from the Zygote pullback, it all blows up, right? So how can I begin to isolate this? So there's a nice trick that we can use, right? So I'm going to define a ref of any inside of main. And what I can do then is I can say main.xx, so this is this reference, right? So I'm going to actually use this global here. And then I'm going to just say it's equal to, let's see, I need yp, I need t, and I need this lambda, right? This is all the information. Now I'm going to evaluate this, right? So if you are evaluating it in the module, see here it says diffuse sensitivity, then this is going to revise, directly update the code, right? Without having to rerun everything, right? If it's not picking up the module, you have to do that. But you just update in place with revise, and now we can rerun this. Right? And you can see that now if I put everything in this order, this means that when I pull this out from XX, I should be able to get exactly the values that were used, but right before the error, right? So, these are the values of lambda, yt that were actually from the run inside of the package. I snatched them up into a global and I spit them back out. So I can actually see everything locally on my computer. And this becomes useful, right? So I can now start to recreate this issue, right? So let me do this from scratch. Right, so you notice that if you just do some commands, you'll get these ... and not everything is printable. But one thing that you should remember is that the show function will always give you something that, or it's supposed to always give you at least something that's always copy pastable. So here I can say, what is y? I just show it. What is p? I just show it. Right. What is t? I just show it. And then what is lambda? I just show it. Right, so these are the values that were actually used inside of the package when the error was found. And I see here that I need forward diff and I need ordinary diff EQ. So as I build my MWE, I'm going to need to say, okay, I need forward diff, I need ordinary diff EQ. Right. In fact, I can go in here and edit the tags, but this is me being a little lazy. Okay, now what do I do with it, right? So what I need to do is I need to do this zygo.pullback call. So there's something with zygo here, and then there's this f, where this f comes from this ODE definition. I'll show it in a second, but so then basically the steps here is you call this and you call this on some function f, and it should recreate this error. So what is f? Well, let me dig in here, right? So f is going to be defined as, well, f is actually where the problem ends up being. So if I look back in the stack trace, right, you're going to see that, hey, there's some non-zygote thing in here. What's the first non-zygote thing? Oh, this is the f that is in use to define the ODE problem, right? So here I can just snatch it right out of the package. I can snatch it right out of the package, and this will define f as equal to restructure of the neural network, right? So remember in neural differential equation stuff, this is the restructure function. So I'm going to grab my neural ODE model, and then I'm going to say p re equals destructure of the model, right? If you're not familiar with flux and the destructure function, this is something that's mentioned in the documentation of using neural ODEs with flux. So okay, so this is now just me isolating everything out. Let's see, what was this error here? Dual was not defined, so let's be using for diff dual. Here we go. And now here you go. So here, this is now a version of that error with exactly the same values and everything that doesn't require even the ODE solver to run, right? I can now go back in and I can say, ordinary if EQ tag, I can actually replace these with nothing, right? So let me do this really quickly. So I could do ordinary if EQ tag, replace this with nothing. I should be able to run this then without ordinary diffie. So boom, now here's a version that doesn't even require the ODE solver that will reproduce this entire error. So this shows you how to kind of pull, so this main.xx, so this ref trick is a very handy way, right? You just make a ref of any, and then you put something into this ref. You know, you can put anything into a ref of any, right? I mean, it could take any type. So here I just put a tuple of all the values and I spit it right back out, and I can use this to be able to grab the REPL. So this shows you quite a few things: how to move through the stack trace, how to make them, how to read these stack traces, how to then generate this MWE, and be able to help someone else help you. I can now copy paste this and say, hey, here's an issue of forward diff and zygote that didn't seem to exist before. And here's how you recreate it. I guess I need the flux for the chain and such, but this will be something such that a Flux developer can work on without having any knowledge or even having installed the differential equation solver. So if you made it this far, thank you very much. If you'd like to find more content like this, I do have a YouTube channel called Parallel Computing and Scientific Machine Learning, which goes into detail in a lot of the aspects of SciML, the different methods and everything, but also a lot of the programming aspects. So for example, I think that a very nice lecture for a lot of people is how to optimize serial code in Julia. So if you want to get more information, please check out this course. Please check out my personal YouTube channel, which has a lot of videos on the methods and such, and a lot of these different videos that go into how do you use Julia effectively in the context of SciML and solving general equations, from optimization to ordinary differential equations to nonlinear systems and all the sort. Thank you.